Okay, so there's a demonstration of a catalyst in action. What was the platinum doing there? Why was it that the platinum caused this reaction to go when it didn't go until we had the platinum in there? Well, to understand that, we need to think about the energetics of this reaction. So here's our starting material on the left. In this example, the starting material was methanol and oxygen. And we've got the product on the right. The product in this case was formaldehyde and some water. And you can see that the product is lower in energy than the starting material. Chemists would say that this reaction is downhill. So you can maybe think that it would be very straightforward to just go from the starting material to the product. But that didn't happen. Until we got the catalyst in there, the thing just quite happily sat there and nothing happened at all. We needed to add the catalyst. Why is that? Well, it's not as simple as just going from the starting material to the product, even though it is downhill. What we have to do is mount this big barrier in between the starting material and the product. It's kind of a hill to climb to do this. We've got to go all the way over this hill until we can get to the product. And that takes a lot of energy. And that means that the reaction is slow. In fact, the reaction didn't go under the conditions I've got there. So I've talked here about things being downhill and about there being kind of a hill in the way. And actually, using that analogy is one that we use all the time. We really can think of this as being a mountain in the way. So if we're in the mountains and we're in one valley, and we need to get to another valley, even though that second valley may be lower, if we've got a mountain range in the way, it needs a lot of energy to get into that second valley. So this is Great Gable. Anybody that's been to the top of Great Gable will testify that it takes a lot of energy to get to the top of it. And the same with our chemical reaction. The product is low, but we've got this mountain in the way. And so we need a lot of energy to go over the summit of this mountain. So what's the catalyst doing? Well, what the catalyst does is provide another route. The catalyst gives us another path through the mountain. And now, rather than having to go right the way over the summit, it cuts a cunning path alongside the mountain. We don't have to use as much energy to get to the product. And since we're using less energy, now we can get much more quickly to the product. So the reaction goes more quickly. We saw that we've got a very rapid reaction of the methanol going to formaldehyde there. So what can the catalyst that does this, what can it actually be? Well, we'll see one example. It could be something as simple as a metal. It could be platinum. And these types of catalysts are widely used in industry. But they often don't give us a lot of control over the chemical reaction. Another type of catalyst would be nature's catalyst. So nature's catalysts we call enzymes. Exquisitely complex molecules, evolved to give very high levels of control over a chemical reaction. But these types of catalysts are not particularly robust. They certainly wouldn't take kindly to being flambéed like the platinum catalyst that I just showed you. So there's a third type of catalyst, and this is the type of catalyst that my research group are interested in. These are called homogeneous catalysts, and these are somewhere in complexity between the simple metal and the enzyme. It's not as complex as the enzyme, but it gives us good control on the enzyme, and yet it's much more robust, and we could use this in an industrial process. So I've talked a lot about getting control in the chemical reaction, and that's also something that's very important. If we go back to our mountain again, we've got our path through the mountains here, and we can take our starting material and turn it into the product. But anybody that's actually been in the mountains will realise that it's never as easy as that. There's never one path. There's always more than one path. The mist comes down, it's murky, it's difficult to find your way. And the same with catalysts. There can be more than one path. So here, the red path comes a little bit lower down the mountain, and rather than ending up where we want to be with product A, we come a little bit lower and we get product B. So we're going to make some product A, but we're going to come a bit lower and make product B as well. So we would say that this catalyst isn't being selective. And what we want our catalyst to be is very selective. We just want to make one product. We want to make product A. the one that's valuable, the one that's of interest to us. So how do we go about getting a catalyst that will give us just the product we want, product A? Well, the way we need to do that is by thinking of catalysts as being kind of a molecular machine. If we've got another type of machine, say we've got a clock, and say that clock wasn't telling particularly good time, how would we get it to tell better time? Well, we would take it apart, we'd look at the different components, we'd try and understand the mechanism of the clock. And then, in understanding it better, we'd try and put it back together and get it to tell better time. And this is exactly what we do with the molecules, which are catalysts. In fact, we even call the study of how they operate their mechanism. We take them apart and we try and understand how to put them back together in a better way to make them more selective. And the first of the stories I'm going to tell you about research in my group relied on understanding this mechanism. It relied on making a catalyst which was more selective. And this first story is about commodity petrochemicals. So commodity petrochemicals are kind of the unsung heroes of the chemical world. These are not beautifully designed drug molecules that are going to cure cancer. You can't go to Waitrose and buy a kilo of a commodity petrochemical. I should maybe explain to the students in the audience that Waitrose is a supermarket where grown-ups do their shopping. But commodity petrochemicals are very much the building blocks of the modern world. Without commodity petrochemicals, the world would be a less colourful place, it would be a dirtier place, it would be a more expensive place. And the commodity petrochemical that we were interested in was 1-hexene. So a very simple molecule. I'm pretty sure the non-chemists in the audience have never heard of 1-hexene. And yet, you will have used 1-hexene every day. This is used in the manufacture of polythene. A typical polythene bag would maybe be 10 or 15% 1-hexene. Tens of millions of tons of 1-hexene made every year. And the way that it's made is by taking a simple, cheap building block that we can dig out of the ground, and in this case, it's called ethene. It's just a 2-carbon molecule over here. And we use a catalyst, and that catalyst will join 3 of these C2 molecules together to make a C6 molecule, hexene. The problem with the existing technology for doing this is that it's not selective. So as well as making C6 that we want to make, we also make C4, C8, C10, C12, 14, 16, 18. We make a whole mixture. Now that's maybe not as bad as it seems, because actually all of these different carbon numbers do have different applications. For instance, the C10 molecules are used in making lubricants. The C12 and C14 molecules are used in making detergents, so going to ferroliquid. Maybe for the benefit of the students, I should explain what ferroliquid is. Something that grown-ups use for doing the washing up. So all of these things have different applications, but still we've got to separate all of these different products. And the amount of the products that we're making doesn't correspond to the size of the markets for them. It doesn't correspond to market growth. What we really need to do here is to make 1-hexene on purpose. What we want to do is just take exactly 3 of these C2 ethene molecules and just make C6. So to do that, we need to understand the mechanism of the existing catalyst. And that's been known for probably more than 50 years. And the mechanism is something like this. Here's our catalyst, just represented by a yellow dot. And that's got this short 2-carbon chain attached to it. If we have an ethene molecule and bring that to the catalyst, that will react with the catalyst and extend this chain to make a C4 chain. And now this 4-carbon unit, this can come off the catalyst, and that gives us C4 product. We call that butene. We can also bring another ethene molecule in, and we can react that with the catalyst, and we can extend the chain by another 2-carbon units, and now have something with a 6-carbon unit. And again, we can bring this off the catalyst, and that will make the hexene that we want. The problem with these catalysts is that they're not selective. The catalyst can't distinguish between the C4 chain and the C6 chain. And maybe A way to show that is with one of these molecular models. So all chemistry students will recognise these. Chemistry students take smaller versions of these molecular models into their exams and then don't use them to get to the right answer. And if we've got a C4, so the red dot here is the catalyst. If we've got a C4 chain, it's pretty flexible. It's going to be very easy just to lose that C4 chain. If we extend this out and we now make a C6 chain, it's no different really. As far as the catalyst is concerned, this is still very flexible. It can't distinguish between the two. And yet we need to somehow distinguish between having a C4 chain and having a C6 chain. How do we do that? Well, the way to do that is rather than having a ring to join these together, rather than having a chain, sorry, to join these together and have a ring. So if we've got a ring, this is much more stable, this is much more rigid. Five-membered rings in chemistry are particularly stable, and we can't lose the 4-carbon unit from this. However, if we extend this out and we go now to the 7-membered ring, so the thing that's got 6 carbons in it, well, it's more stable than the chain, but it's much more flexible than the 5-membered ring. So now the catalyst can distinguish between when it's got 4 carbons attached to it and 6 carbons attached to it. And if we look at that on a slide, what we're doing here is having our catalyst reacting with the ethene to make a 5-membered ring. This 5-membered ring is stable, but it will react with another C2 ethene unit. And if we react with another C2 ethene unit, we get to the 7-membered ring. The 7-membered ring is less stable. The catalyst can distinguish between the two, and this 7-membered ring will lose its 6-carbon unit, give us our hexene, and regenerate the catalyst. So let me just show you one of the catalysts that we designed that will operate via this mechanism. Here's a recent example. These types of catalysts are based on chromium, and these are extremely selective in making this valuable product 1-hexene. These will make 1-hexene with greater than 90% selectivity. Compare that to the mixture that we've got before. This is a much more efficient way to make 1-hexene. In fact, it's such an efficient way to make 1-hexene that Sasol, the South African chemical company, are actually building a world-scale chemical plant based on these types of catalysts to produce 1-hexene. And this plant is in Lake Charles in Louisiana in the US, and that's going to begin operations next year, and it will make 150,000 tons of hexene every year using these types of catalysts.